Hey everybody, and welcome to the beginning of chapter D. This chapter, we're gonna wait, I guess he's over there. This guy, see that guy back there? We're gonna dig into the periodic table of the elements. Why? Well, I don't know if you picked up on it, but the whole time, most of the time during chapter 1, I kept going, well, hey, over at the periodic table. Well, hey, over at the periodic table. Well, hey, if you don't know that, just look it up on the periodic. There's so much information contained in that periodic table. It's kind of incredible. So we are going to spend an entire chapter looking into how that periodic table was made, because it's weird shaped. Like it's it might be nicer if it was like put into a grid, but it's not for a reason, because in that weird shape there's hidden information. And if you know how to read the periodic table of the elements, you can gather a lot of information about each atom, and in doing so you can tell how the atom's going to behave, how it's going to act in a chemical reaction. You can get an idea of chemical physical properties, blah 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 blah, all kinds of sciencey stuff. So that is what we are going to do starting right about now. All right, yay, chapter 2, the periodic table of the elements. So here we go. For a really, really, really long time, there were only a few elements that were actually known, like gold and copper and things like that. Now here's the deal. This thing, this guy right here, gold, man, this thing, that's the stuff. Because listen, for a really long time, gold was where it was at, like it's really valuable. Wait, oh yeah, still. So here's how it worked. If you've ever wondered, like, why is it gold that's so expensive instead of, like, I don't know, how about nickel? Nickel's very pretty. Or copper. Copper's very pretty and it's useful. Gold, yeah, well, here's the deal. Gold is one of the very few elements that you used to be able to find just sort of like sitting out in like a riverbed or something, and you could like actually pick up a nugget of it. And when you would do that, you could take that nugget of this really beautiful, shiny metal. Now, when I'm saying this, we should put it on our brains of like ancient people who have never seen technology before, ever. These are still like hunter-gatherer type people. And they find this really shiny thing, and in nature there are very, very few things that are actually really bright and shiny. Like almost all the bright and shiny things that like you and I come in contact with are man-made. So go back way to the ancient times, something shiny, pretty nice. Now gold, not only is it really shiny, it's malleable. In other words, it's soft and you can like smoosh it into a shape. And so if you're like an ancient person and you've never seen anything shiny, check 1, gold is really shiny. Not only is it really shiny, but you can shape it into something that you want. Check 2, and here's the really big check 3. So ancient dude found a hunk of gold, squeezed it into a shape that was very special and important to him. Tied it around his neck. He took it with him everywhere. One thing that never happened to that piece of gold is it never got old, it never rusted, it never tarnished, it never ever decayed. Which if you're like an ancient person, dude, living in the nature in like the natural world, dude, everything decays. Everything. There's nothing that doesn't decay or decompose. But here's this little shiny golden nugget that has not once shown the test of time. It's not grown old. It's not started to decompose. It hasn't gotten moldy. It hasn't gotten nothing has happened to it. So he gave it to his son, and then that person gave it to his son, and soon they pretty much caught on to this stuff was pretty special. And actually gold is pretty special in that it doesn't really tarnish very well or very, very easily, which is why on many of our electronic pieces of equipment, like particularly where there's like plugins, things are coated with gold, like real gold. The reason being is that it doesn't tarnish. It won't rust or anything like that. So that is amazing. So there was gold, there was copper, right? Like they were able to make some metal things. And for the longest time, like people thought that things were made of like fire, earth, metal, water, and wood, and in different like varieties of these things is what made things to be what they were. Kind of made sense though, because you took wood, right, and you could burn it, and wood made fire, right, and where did wood come from? Well, it came out of the earth. There's all, that's where trees come from. So there's a good reason for these ideas, but time went on, and so by 1700 there were only 13. there were only 13 elements known in European American history. So so as science sort of progressed, and as you saw, like we learned about electrons, we learned that atoms were mostly empty space. There was a big push to find out what elements were out there, because we discovered atoms. Like we realized that there are these things called atoms, and each element, we discovered that each element, and it looked like all of those atoms were exactly the same. So the big question was, well, how many elements actually are there? Like if elements are not this stuff, if this isn't what elements actually are, and elements are these like atom things, how many atoms are there? Because we originally thought there were only 5 elements, and you're telling me now there's like 13? So the push was on. Like, what is our world made out of, right? So they started digging. And so by the mid-1800s, there were 70 elements that had been discovered. But people knew that there were more. And there was a big push to find out what were those elements. Now there was more than one like motivation here. Yes, there was the academic like seeking of knowledge, trying to understand our universe. There's also stuff like the reason why you have a cell phone, the reason why you have like AirPods is because we have discovered new stuff and new ways to put new stuff together. Do you understand what I'm saying? So being able to make really good alloys or mixtures of metal that can be drawn incredibly thin and can carry electricity really, really well is what made cell phones able to happen. So in the olden days, as they're able to discover new things, they're able to make new products, which is going to make somebody really rich. You know, the next person who can make a super strong metal for a wagon wheel that doesn't rust and go bad in 2 years, they're going to make a lot of money selling wagon wheels. And this is the way it's been since the beginning. During World War II, it was molybdenum steel, which is what changed like firearms like forever. Molly steel, baby, right? So the push was both academic and economic. So there was a push to get to the place where we could discover all of the elements. And so as we were discovering them, we knew that we needed to find some way to organize the elements. And this is the real thing here for the scientists and whatnot, because we figured at the time that if we could see the pattern of the elements, that would be it. That would unlock the secret of the universe. We would unravel the mysteries of nature, and we would understand Mother Nature. Finally, we would be able to control and understand all of Mother Nature, if only we knew the patterns of the elements, right? Well, that was the idea back in the day. You see, people still feel very much the same way right now. So anyway, the push was on to try to find a way to organize all these things. And here comes Dmitri Mendeleev. I want you to look at that guy and see the tenacity it took to finally organize it too. Anyway, Dmitri Mendeleev. This guy was brilliant. He was a Russian chemist, and he originally arranged them according to atomic mass. Now, here's the story. He was... Back in the day in Russia, there were 2 kinds of Russians. There were dirt poor and there were uber wealthy. And you were either dirt poor or uber wealthy. He balanced. He was right on the edge, right? His father was an aristocrat, but was killed. He was left with just his mother and lots of children, and blah blah blah. Finally, he was able to go to college, and he had this job finally. And as a chemistry professor, and back in the day, you had to write your own books. And one of the things that he needed to do was to organize the elements so he could teach them in a logical manner. And he had to write his own textbook. And he was stuck, and like, what is he gonna do? And blah, blah, blah. So he decided. It actually came to him in a dream, like no lie. He was like pining over it for like a very long time. He had to do this, or he was going to be out of a job and probably, freezing to death somewhere out in Siberia, because Russia gets cold, man. And so he had to find a way to organize them, but he couldn't because there was no real clear way. All of science was trying to do it, and no one could see it except him. And everyone's like, yeah, atomic mass, whatever. But dude, he didn't have all the elements. Like, that's the problem, is he didn't have all the elements to organize. So this is what he did. He left blanks for the undiscovered elements. And dude, this is the thing. Dude left blanks. He was able to see the pattern even though he didn't have all the pieces. Like that is incredible. And so you'll see, like down here, he left this empty. and he like left this empty, right? And he kind of left this empty. He left this completely empty, right? But he guessed. He's like, well, I think that it's going to be according to atomic mass, but if my guess is right, I need to leave this and jump over to here, right? Because there's probably one here. And this is the new line, the new group, and we probably need to skip 1, 2, 3, 4, 5 before I can start with this one. So he was able to see the blanks, these empty spaces. And not only did he just leave gaps, but he made predictions about what the chemical and physical properties would be for those unknown, unseen, undiscovered elements that no human had ever borne witness to. Ooh. Well, dude, it turns out he was right. Which was like what? Like that. Dude, that blew the heads off of like all of science. They're like, how can you just magically guess at the chemical and physical properties of elements that don't even like nobody, no one, how wow. Like some people thought that he was like touched by the gods and was a soothsayer and could like had ESP and could like see into the future, or was like had some mystical connection to the universe or something. Really, no, the guy was just really, really brilliant. And he was truly a brilliant scientist. However, as with all theories in science, or theories being explanations, or like, the current way we explain things, in this one there were some small problems, right? Like these issues that just didn't quite match. And so for a few elements, like hold on guys, like cobalt, nickel, argon, potassium, tellurium, iodine, there were just a few of these things. It just didn't quite line up with Mendeleev's predictions, right? So we knew there was a chink in the armor. However, I want you to look at this. Look at that dude's face. Right? Somebody tried to argue with him. They're like, Dr. Mendeleev, I think you might be wrong. And that dude, this guy right here, is the one that yelled at him. Now, here's the thing, man. We got stuck in this place for a very long time, where Dmitri Mendeleev was kind of a mean person. He was not nice. Anybody who questioned him, he would just squish them. You're not allowed to question Dmitri Mendeleev. He is right. That's the way we've always done it. And so we kind of got stuck because that's the way we've always done it. And nobody wanted to question these little, issues until this young man, right? This guy. His name was Henry Moseley. And fun fact, he was a student of our good friend Rutherford. Yeah, because Rutherford was that good. Now, Moseley could have been as good as Rutherford. He was that good. And Moseley was kind of like digging into the nucleus of the atom, trying to figure out what the heck is going on. And he's got this periodic table, and it's just not working for him. So he's like, I think what I see in the nucleus are protons. And so he went back to Rutherford, and he's like, Rutherford, my experiments are kind of making me think that there's these little positive particles in the nucleus. And Rutherford, much to his credit, was kind of like, I don't know what you're talking about, Moseley. I don't really understand how this works, this experiment that you're doing, but I trust you. You're a smart dude. Go for it. And so, Rutherford gave Moseley his blessing to just, go do his thing. Moseley did his thing and realized that if you ordered them according to atomic number, which he realized was the number of protons in the nucleus, he was like, oh, all the problems of Mendeleev's table went away. All went away. And this dude was in his 20s when that happened. It was incredible. Problem, Mr. Moseley, outsmarting the smartest man on Earth, World War I broke out, and he was British, Moseley was, and Britain was like, please stay in the lab and help us with your scientific brilliance. And Moseley was like, I'm a man. I'm gonna go fight in the lines. I can't sit in the lab and do nothing. He literally got to the front lines, hopped off the truck, and on the first day was shot in the head, and then wasn't able to help anybody. It was ridiculous, man. One of the most brilliant minds in the alive on the planet, lost in the blink of an eye because he needed to go fight. Pretty much a bummer. But anyway, he still won the Nobel Prize beforehand, so come on. Not a bad run, even though it ended in his early 20s. And so this is what we use today. We use atomic number. And what this young Sir Moseley was able to figure out and learn is this thing, periodic law. And here's what periodic law means. It means the properties of the elements are periodic functions of their atomic numbers. What? Now here it is in like red. So here's the thing. We've got this one right here, periodic law, said in like fancy academic terms, but this is what I want you to like. That's in like normal terms. So basically what Moseley saw is that when you lined elements up according to their atomic number, there is a periodic repetition of their chemical and physical properties. In other words, it's like if you measured atomic radius, right? And if you lined all the atoms up like this and then graphed atomic radius, it's like atomic radius will go up, 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 boom, and then drop down almost to where it started, and then go up, 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 boom, and then drop down to almost where it started, and it kept doing this over and over and over, periodically. That means like repeatedly, over and over, like so over a period of time, things repeated. And so what Moseley did is basically once things started repeating, he hit the enter button and went on a new line on his periodic table, and that's bam, how we got the periodic table of the elements of today. And so a quick refresher, this is nothing new. You guys already know all this. Information that is on the periodic table of the elements. Atomic mass. Now you remember, this is atomic mass. And remember, it's the average. It is average atomic mass. Not the mass of like one individual atom, but the average mass of all the copper atoms that you will have when you scoop up a sample of copper or any other element. Now, atomic number, if you remember, right here, this is the number of protons. Electron configuration, we just talked about that earlier, right? Number of shells, number of electrons in each shell. We read it from left to right going this way, so it looks like copper has one valence electron. Right? And there's this other thing over here called, wait, let me get you over here so you can just go over here. Oxidation number and charge. So oxidation number and charge. We will talk about what oxidation number is. It's really similar to charge, but that's right here in this corner. And this is not to say that copper is always walking around the world with a +2 and a +1 charge. It means copper can make two ions. One of the ions will have a +1 charge. Another form of an ion, or different ion that it can make, is a +2 ion. So copper has two forms when it makes an ion. It can make two different kinds of ions, in other words. Copper +1, copper +2, each being as different as one possibly could be. And then, of course, the chemical symbol. And if you notice, it is always capital first, then lowercase. So, for example, I'm going to write over here for sodium. Sodium, this is one that everybody likes to do, is Na. That is the proper symbol for sodium. This I cannot accept. So here's the deal. Uppercase, lowercase, good. Uppercase, small uppercase, not happening. Not happening. Oh, wait, I can also accept this. Large uppercase, large lowercase, I can even let that fly. But you may not have an uppercase for the second letter. Why? That way we know what we're talking about. Because many elements have only one letter for their symbol, and so we have to be uppercase, lowercase. That's it. It has to be uppercase, lowercase. No exceptions. I'm real sorry. That's terrible. This next thing, I'm just going to mention this real quick, just because everybody ends up asking me, hey, what's that what's all that stuff? So here's the deal. At the bottom of your periodic table, there are all these elements that look like this. UUN, UUU. So these are elements that at the printing of this periodic table were as of yet unnamed, because we don't discover elements all by ourselves anymore. Like, science is not like one dude sitting up in a laboratory, like mixing things in a flask under candlelight. Dude, chemistry and all science is a huge like team endeavor. Like, when I was working in a lab, I had a lab in Pennsylvania, and we would talk with folks in California, Canada and France constantly, because we were like always working together. And that's how it is with all science. Everybody's working together. So to discover this new element with an atomic number of 110, it takes a particle accelerator, of which there's like 2 or 3 in the entire world that operate, and it takes a team of like people from all over the world, like 10 years to dig through this data. And so once it's dug through, it's like a team, huge numbers of people, so it's not like one person gets to name it. So what happens is big brain people, like scientific community, all get together, and I think once every so often, and then name them. But in the meantime, they use this abbreviation so we know what we're talking about. And it's just these are just initials for, I think it's Greek prefixes for numbers. So like this one, U, this means 1, 1, 2. So 1, the prefix for 1 is un. So there's 1 would be un. There's another 1, it would be un. And then the prefix for 2 is bi, and then you end it with nium. So this is binium. This is unium. And this is zero nil nilium. So anyway, there's silly names, but they're only temporary. So yeah, no. It's just that's why that's there. So there you go. Okay, so arrangement. The overall arrangement of the periodic table is ordered by atomic number, right? That's the main thing that we use to arrange the periodic table. And different rows and columns are determined by the law of periodicity. So in other words, when those chemical and physical properties start to repeat themselves, we start a new line. Got it? And what we get are horizontal rows that we call periods. So this is one period. It is a horizontal row. This is another period. It is a horizontal row. Do you guys get what I'm saying? Awesome. And so a horizontal row is a period, and I always remember it because a sentence, right? Like we read a sentence this way, and then at the end of the sentence, boop, you put a period. That's how I remember that a row is a period. Now here's the deal. In a period, you have the same number of shells, right? That's really important because that determines, that tells us a lot about the chemical and physical properties. And the number of valence electrons increases by 1 from left to right. So you see, there's lithium, there's 1 valence electron. Beryllium, there's 2. Boron, there's 3, then 4, then 5, then 6, then 7, then 8 valence electrons. And then everything repeats itself because, we already hit the 8, and 8 is great. You dig? Oh, and there are also 7 periods. So each period is numbered. So this is period 1. See this word right here, how it says period? So that's period 1. That's period 2. That's period 3. That is period 4. Period 5. So on, so on, so forth. And then, so here's the deal. If the number of valence electrons for each one of these elements is different, what can you tell me about the chemical and physical properties of all the elements in a period? Are they similar or are they different? Well, different number of valence electrons, different chemical physical properties. You already knew that, right? Moving on. Vertical columns. Vertical columns, these are called groups or families, right? A group or a family or a column, 3 words, same thing. Here is a group or a column. It goes up and down, right? Up and down. Oh, here's one too, there, right? So there are your 3 examples of 3 different groups, columns, or families. So, here's the deal. Same number of valence electrons. Y'all, what can you tell me about the chemical and physical properties? You're right. They're going to be similar. Yep, absolutely. They're very similar chemical and physical properties. So, carbon and silicone both have very similar chemical properties, right? Carbon can be made into all kinds of weird different shapes. Like, look at anything that's alive or is out in nature. It's all carbon-based. Like, and look what the shapes you can make with glass and like silicone putty. You can make any shape you want. It's amazing. They're very similar. Sodium and potassium, these are all really, really, really similar. That's why, like, Gatorade will be like, oh, 500 milligrams of sodium and 600 milligrams of potassium, because sodium and potassium behave very, very similar in our body, and they help us with our sodium-potassium pump and our nerve cells and all that kind of good stuff. They behave really, really similar, right? So there it is. Similar chemical and physical properties in a group or family. And that's also why we call it a family, because people in a family kind of look similar. Well, elements in a family kind of look and behave similar. That's just how that is. Oh! But how is that it, man? It's not even 45 minutes yet. You guys are getting off easy with this one, but only for today. So here is what we are going to be doing. It's how is the periodic table arranged? That's the worksheet that is associated with this. We're going to work on that, and I hope you guys figure some stuff out. Thanks for tuning in, and thanks for learning. Thanks for learning. Apparently I need more coffee, and I will see you guys very soon.